In this video, we are going to discuss different types of chemical reactions and how to recognize them. And we will initiate that discussion by talking about precipitation reactions. Precipitation reactions are those reactions in which we form a precipitate or an insoluble compound. Remember that we talked about soluble and insoluble compounds, and we had several tables in chapter 9. Here's the flow chart that should hopefully help you. So we start by looking at the cation and what type it is. If it's one of these, then it's a soluble compound. If no, then we look at the anion, and so on and so forth. So you have a flow chart that you can follow to determine whether compounds are soluble or not soluble. And we talked about them in the previous chapter, but make sure that you review them and you use those rules to determine whether you have soluble compounds or insoluble compounds. Precipitation reactions occur with ionic compounds, and that's when we're going to form insoluble compounds from different ion combinations. And here's a flow chart for insoluble compounds. So if I have one of these, carbonate, the phosphate, the chromate, or sulfide, right? If they're paired up with any of these, then they're going to be soluble. But if not, then if they have this anion but a different cation than these, then the compound is not soluble. If these are not the anion, but the anion is hydroxide, well, are they paired with one of these ions? If these are the cations that are paired with the hydroxide, then the compound is soluble. But if not, then it's not soluble. Here's a sample problem for you to try. Classify each of these compounds in soluble or insoluble in water. You have AgNO3, CaSO4, and K2CO3. Use the charts, the flow charts, to determine whether these are soluble or insoluble. We also talk about double replacement reactions. In these reactions, we have on the left-hand side, we have two soluble ionic compounds. So the reactants are going to be soluble ionic compounds, which are made up of positive ions like the sodium and the lead here, and negative ions like NO3 minus and I minus. Then what happens is I take the positive ion of one compound and pair it with a negative ion of the other compound. So sodium here gets paired up with NO3. Note that do not be tempted to change the charges on the ions. Na is a +1, will always be a +1. NO3 is a -1, will always be a -1. It will not be NO3 2 minus, but it will be NaNO3 because it's a +1 -1. They cancel each other out. Here's the compound. Now that 2 in front tells me I have 2 of each. So 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates. This doesn't correspond to the charge. This tells me that I have 2 nitrate units. Now lead is a 2+ ion here because nitrate is a -1. 2 of those gives me a -2. That means that lead has to be +2. So lead is a +2, but iodine is a -1. So when I combine those two together, it will be PbI2. I need 2 iodides for every lead. 2 times -1 is -2, plus 2, I have a neutral compound. Once you establish the correct formulas of the new compounds, when we balance these, do not change the subscripts any longer. Just put coefficients in front of the molecules. Once I write and I balance this, I also need to figure out whether I made two soluble compounds as products, or if one of them is insoluble. Well, if I take NaNO3, whether I'm looking at the cation or the anion, there are no exceptions. Sodium compounds are always going to be soluble, no matter what sodium is paired with. NO3 ions are also, so compounds that have NO3 are also very soluble. So either way, this is a soluble compound. Lead 2 iodide, however, if you look at iodides, those are soluble unless they are paired with lead 2+. And that's what it's paired with. So lead 2 iodide here is an insoluble compound, and that's why it's got an S for solid next to it. Note that this is called double displacement reaction because I'm displacing both positive and negative ions. And I'm rearranging everything. So I'm doubly displacing both positive and negative ions. Okay, so once we establish the correct formulas for the new ionic compounds, cross the charges to figure out what the subscripts are going to be. But once you know the subscripts, do not mess with the subscripts any longer. Balance using the coefficients. Once we do that, then you look to see if the products that you made are going to be soluble or not. If not, they will precipitate out of solution, just like lead 2 iodide did here. And we do those by following the solubility rules or the guidelines for the ionic compound. When we talk about ionic equations, so whether it's precipitation reactions or double displacement reactions, we also talk in terms of complete ionic equation or net ionic equation. A complete ionic equation is that equation where the compounds are written as they will exist in water. However, ions that appear on both sides of the equation of the arrow are called spectator ions, so they will appear exactly the same on both sides. And if they're exactly the same on both sides, they're called spectator ions. They don't participate in a reaction. And they cancel one another because they appear on the right-hand side and the left-hand side. Just the same form and the same number of both, so they can cancel each other out. Then what is left over once we cancel those spectator ions out becomes your net ionic equation. So it does not have spectator ions. Here is an example. If I put sodium sulfate in water, it's going to split into the sodium ions and the sulfate ions. Note that I have 2 sodium ions for every sulfate because sulfate has a 2- charge, whereas sodium has a +1. So in the formula, this would be Na2SO4. But once I put Na2SO4 in water, it will split into individual ions. Do not be tempted to write Na+2 because you have a 2 as a subscript in Na2SO4. Sodium ion will always be +1, but that 2 as a subscript comes in front as a coefficient of the ion then. So I have 2 sodium plus SO4 2- aqueous. And then if I mix barium hydroxide with that, barium hydroxide is Ba parentheses OH close parentheses 2. Because barium has a 2+ charge and OH- has only -1. So I need 2 OHs to balance my barium. Now, if I do a double displacement reaction here, if my sodium was paired up with the SO4, Well, what's the other? What is the other negative ion that I can pair sodium with? Well, that is the hydroxide. So I can write sodium hydroxide. However, sodium hydroxide is soluble in water, so it will appear the same way as it is on the left-hand side. So even if I wrote NaOH together, that still would split up again to give me sodium and OH minus. That appears exactly the same on this side as well. What happened to the other pair? Barium pairs up with the sulfate, giving me barium sulfate. Now note that I don't have to write any other coefficients because the 2 plus and the 2 minus, this is a 2 plus and a 2 minus, they cancel each other out if I write them BaSO4. And if I follow the rules, the solubility rules, you will find that sulfates are soluble except if one of the exceptions is barium. And therefore, barium sulfate is insoluble, so I put an S next to it. Now, because sodium and hydroxide appear the same on both sides, I can cancel them out. This up here is my complete ionic equation. But then what is left over? I have barium 2 plus SO4 2 minus, giving me BaSO4 solid. This equation here is the net ionic equation because I don't have the spectator ions. I canceled them out. I only have those ions that participate in the reaction to give me that precipitate or the insoluble compound. When we balance ionic and net ionic equation, we write the molecular equation first without splitting the ions. Then we predict what the products will be by assuming that the cations are flopping, so they're changing anions. Once that happens, you can write the complete ionic equation by separating those that are strong electrolytes into what makes them up, those ions that make them up. The net ionic equation then will be the equation that is left over when you cancel the spectator ions that appear on both sides of the equation. Here is a sample problem for you to try. Write the molecular, complete ionic, and net ionic equations for the reaction that occurs when you have aqueous solutions of lead 2 acetate, and here's the formula given to you, lead 2 acetate, and calcium chloride, CaCl2. These are your reactants. Write molecular formulas, so don't write ions yet. Write molecular formulas, although you do have to use the charges on the ions to figure out what the correct molecular formulas are going to be. And then once you write the molecular equation, balance it, then write the complete ionic equation, so split everything into ions, cancel those ions to get the net ionic equation. So those ions that appear on both sides exactly, cancel them out, and what's left over will be the net ionic equation. The last bit of this video is going to be dedicated to those reactions that produce gas. Okay, some of the reactions that we've already talked about can form gaseous products that bubble out of solution, especially when we're mixing acids and bases together. So here is an example. HCl is an acid and Na2CO3 is a base. So when we put these together, we form NaCl. So NaCl, H2CO3 which H2CO3 can then go on and break down into H2O and CO2 gas, which escapes the solution. Then H2CO3 plus 2NaCl, right, gives me NaCl, but then this H2CO3 breaks down and gives me H2O and CO2, which bubbles out a solution. Here's a sample problem for you to try. Identify the products of this reaction, then write a balanced chemical equation. Note that, so what I'm doing here is I'm swapping, right? I take the sodium and I pair it with the chloride, the hydrogen with the HSO3. However, the H2CO3 breaks down right away into these two compounds, and this one is a gaseous compound, so it will bubble out a solution. These are 2 out of your 3 products. So go ahead and figure out what they are, what the third one is especially, and then balance the chemical reaction.